Tack så mycket. Okay, hello. Thank you everyone for coming here. We've done a couple of experiments combining AI with traditional mathematical modeling and optimization. I would like to share some of these results today. With that great presentation, I don't think this slide is necessary, but to put a face, so I am Alexander.
And yeah, I'm Jacob, machine learning engineer at Jeppesen for flight.
Good. So, quick rundown of the presentation. We'll touch on the world of aviation, some of the common problems they face, how we help to solve these using optimization, and then lastly, how these solution methods were combined with evolutionary algorithms to improve them even further. So, every airline company is quite different. There are some problems they all face. They have a set number of aircraft, crew, flights they need to operate, and they would most likely want to do this in an efficient way. Before we get into it, there are a few terminology we'd like to go through. So first we have a tail, and for anyone curious, it's called, the aircrafts are called a tail, and it's due to the identification number being printed at the tail of the aircraft. Then we have crew. This is a catch-all term for the people operating aircrafts. So this is flight attendants, first officer, captains, etc. We have a trip, and this is a combination of flights starting and ending in the crew's home base. And then lastly, we have a roster, and the roster is a combined schedule of all the flights you will perform over the planning period. And this can also be called a column, and a column then is a mathematical representation of the rosters. These are some of the airlines that we are working with. If you have a look, I'm sure you recognize some of them, maybe even flown with a few. And why we exist and how the airlines are spending their money is roughly outlined here. So we have taxes. This composes around 15%. Not much we can do about this. We have fuel and labor. Combined, this is the largest expense of every airline. We have others. This is operational cost, maintenance, etc. And then lastly, we have a profit of around 1%. So we are focusing on improving these two areas. And as an example, if we were to utilize our crew more efficiently and get this cost down to 17%, we've effectively doubled the profit of the entire airline. So the entire process and what we do. So on the far left, we have long-term planning. This is to make sure that we have enough hardware, tails, flights, crew sometime in the future to perform our flights. This can be anywhere from several years to a couple of months. And as we move further to the right, we get closer and closer to day of operations, and this is where we actually perform the flights that we have planned. And I work in, first off, combined or divided into three different categories. So we have flights, fleet, and crew, all being optimized in a different way. Now, I work in crew rostering. This is where we build the optimization software that helps airlines to produce these rosters every month. And a small example of this could be seen here. So we have a couple of airports we would like to visit. We have a crew Emma and a tail. So first off, Emma makes her way over to London before continuing on and going to Greece. Arriving at Greece, Emma has worked her scheduled time, so she needs a rest. But the aircraft doesn't really need the same type of rest, so on jumps Johanna. And Johanna takes over the aircraft, makes her way to Germany. Emma, however, would like to get home. So another tail arrives, she jumps on that, works another flight, and then finally going back to Gothenburg. And thus Emma has completed a trip starting and ending at the same base. And judging by this, it doesn't look too complicated, but as we start to introduce more and more crew, more and more trips, this problem grows quite rapidly. So for a very small example, where we have 10 crew and 50 trips, we have around 10 to the power of 60 possible solutions. And if we take our largest customer, they have 22,000 crew, with 190,000 trips that needs to be rostered, and this is done every month. So if we were to brute force this, trying every single combination, we would have to go through around 10 to the power of 500,000 different solutions, which is crazy number, hard to comprehend. But if we try to put it into some sort of perspective, the number of atoms in the observable universe is estimated to be roughly 10 to the power of 82. So yeah, obviously this needs to be tackled in a much more structured and smarter way. And on to optimization and what we solve to, or what we use to solve this. One definition of optimization could be to do something as well as possible. And how we tackle this problem is that we set it up as a optimization and an objective function. And a colleague of mine told me that for every equation you show during a presentation, around 15% of the audience loses interest. So when we're done with this section, please raise your hand if you're still here. But yes, optimization, we want to minimize the objective function. This is the sum of all the rosters for a planned period. We need to take some things into account so we can have binary constraints, and this is to make sure that one crew works one and only one roster every month. And these constraints and rules can come from pretty much anywhere. Much of it is regulated by countries' laws. We have regulatory bodies. In Europe, it's called EASA. In North America, United States, it's called FAA, and so on. And these are basically used then to help guide the optimizer to good and legal solutions. So if we take one example, we can have this rest day. This can be modeled in a few different ways. This time we can say it's a soft constraint, meaning that we are allowed to break it, but by doing so we need to pay a penalty. So the overall roster becomes less attractive in the global solution. And these go on and on. We can have coverage constraints, making sure that we work enough but not too much. Language constraints, making sure that everyone working on a trip. And it goes on and on. So yeah, quite a big modeling. And what we're doing is that we're basically trading problem size for problem complexity. And now that we've made the problem so easy to solve, we can use column generation to solve it. And shortly, what column generation is that we are generating columns, which are then representations of rosters. We feed these into the optimizer, where we solve the problem, we learn from the problem, and as it's an iterative method, we can generate more columns that we will know improve the overall solution. And this is done several times until we find a good enough solution. And the generation of these columns is partly done by shortest path solvers. And for this example, so every green node is representing a trip, starting and ending at the crew's home base. We might have a few pre-assignments. So for this, it's training, and this forces the optimizer to include this node into every traversed path through the network. And then every edge is also assigned a cost. For this example, we only have one cost. It gets quite cluttered if every edge were having its own cost. And then by solving this, we are saying that the shortest path through the network corresponds to the cheapest roster. We are generating several rosters or roster candidates per generated network, usually around 5 per crew. So, as I said, we can learn from this problem. So, if we notice that the edge that costs 500 is very often part of attractive roster, we can artificially lower this cost to be less expensive, and thus making it more a higher chance for the optimizer to include it. And there are several ways of solving this. I'm sure you recognize some of them. So we have Dijkstra's, Bellman-Ford, breadth first search, A-star, and then my favorite, the random traverser. And this is basically going to one node, randomly picking which node to go to next. And we do this until we reach the end of the graph and not caring about cost or constraint at all. And this is what we would like to see, how AI could improve. So we fed this random traverser to an open evolve. And more to talk more about this, we have Jacob.
Thank you. I guess green is good, red
Green
is
is
bad.
good.
Okay, so once again, I'm Jacob. I'm part of the AI team here at Jeppesen 4Flight in Gothenburg. And you could say that our team's role in Jeppesen is to enable others to work with machine learning and AI. So our strategy is to try not to centralize these capabilities in only one team or a few teams, but rather to encourage everyone to get familiar with these. And as Alexander said, we make optimization software for the airline industry, and they need that because the problems are very hard to solve. They're huge. They have a lot of constraints facing them, like laws, union agreements, and even preference from the crew that is flying. And so therefore the optimization algorithms lying under this is super important for us and is highly connected to the value we then can deliver to our customers. So in that context, our teams, mine and Alexander's, ran an experiment together where we aimed to make our optimization algorithms even better. And we tried to do this with a framework called OpenEvolve. And what OpenEvolve does is that it aims to iteratively improve algorithms or code by combining evolutionary algorithms with generative AI. So I'll get to the combination soon. I'll briefly just touch upon the two points here before. So let's start with evolutionary algorithms. Maybe hand up. Have you heard about evolutionary algorithms? Yeah, good. So for those of you who haven't heard about evolutionary algorithms, they are stochastic optimization algorithms. And they are inspired by, meaning that they are random, by the way. And they are inspired by natural selection in biology. And the idea there is that you have a population, and all the individuals in your population has a fitness score, which basically defines how good they are at solving a specific problem. And you select the best individuals in your population, you mutate these to create new offspring, and then you evaluate the offspring, and then the loop goes on and on and on. And you repeat this, and your population slowly improves. Sorry, I should have clicked. You get to see a little cool graphic. And in a classical evolutionary algorithm, you would usually evolve something like a vector or a graph or similar. But what is really important is that you have this mutation operation which randomly tweaks the individuals in your population. So the mutation operation will randomly tweak the population. And this, of course, if you do random changes to your population, sometimes this is gonna, of course, mean that you end up in a worse solution than before. But the key part here is that sometimes your solution will become better, just like real evolution. And this is what helps these types of algorithms not get stuck in local optimas, but rather keep looking for global optimas. And in addition to mutation, you can simulate other biological events like breeding, where you would take two parent solutions and you would mix them and create an offspring. And these types of algorithms are completely blind, meaning that they don't really have any understanding of what these changes mean. They just do it randomly. And the only thing that the algorithm actually really understands is which solutions perform better than others. And these have been around for quite some time now, so they're nothing new really, as opposed to the newer large language models that we all are using now, or I'm using them a lot and I like them, and I bet everyone here are using them as well. But with their basic capability being inputting and outputting text, they do, however, have a lot of known shortcomings, like not having any long-term memory or be able to do tool calling or yeah, you name it really. So what is done there is that you add all of these other capabilities, all of these other puzzle pieces around them to make them more complete and more usable for our different use cases. And I would say that combining large language models and evolutionary algorithms in this way is sort of a new way to think about these whole systems. So I'm getting the timer waved at me, so let's continue here. So the combination between Evolutionary Algorithms and Generative AI we did with a framework called OpenEvolve, as I mentioned, and that is an open source implementation of what DeepMind calls AlphaEvolve. And what it basically does is that it aims of keeping this whole evolutionary algorithm structure with the populations, fitness evaluation, and offspring and all of that. But now we change these graphs or vectors that we had previously, and we want to evolve programs or algorithms. So our new population consists of programs, i.e. code, and the mutation operation that we will do to our individuals are now LLM-informed code changes. So we have programs, the LLMs will mutate them, and we also then have to define specific metrics to tell if we find a better or a worse algorithm than what we had before. So the main idea here is that you give an initial program, and then we try to evolve that program or that algorithm to become better at solving a task. So high level, this is what it looks like. So we start with defining our initial program that we want to evolve. We define a way to evaluate it and metrics. We sample parents or a parent program from our population grid. And we use these parents or parent to, we use their code, we use their metrics, and we can also include things like inspirational programs from previously when evolving. And we add this into a prompt, and then we come to the mutation part, where we actually make a code change or change our individual. And so we will send this prompt to the LLM, and then we will receive a code change or a full rewrite of the code. And the cool thing here is that you're not really limited to just using one LLM, but to induce more diversity in your solutions. You can also use a full ensemble of many different LLMs trained from different providers or whatever. So you have a lot of different ways of attacking the same problem. You're not only limited to just evolving tech code either. You can evolve anything that the LLMs can generate, of course, as long as you have a good way of evaluating if it's doing better or worse. But let's get back to the example. So then when we have mutated the code, gotten a new offspring, we want to evaluate that. And if it's competitive enough, we want to store it back in the population grid. So where we store it depends on the niche implementation of that program, the traits that it has. And if the place where it belongs in the population grid is already populated, we will have to make the two programs compete with each other, and we will only keep the winning one. And then we will loop over this over and over again in parallel. And that's how we evolve the algorithm. And a dire attempt at illustrating something. It's a really hard sort of experiment to show something interesting in. But here is a visualization, and I understand you, of course, can't read this. You're not supposed to. The only thing I want to visualize here is that there is an initial program that we have defined, and then over whenever we find a better one, we make these code changes, and this basically represents the best program found so far. So that is the idea, very much like if you have worked with evolutionary algorithms. This is it, but for code. So maybe now you can set the expectations a bit around what performance we saw when we did it for our own customer data.
Yeah, thank you. I see we're quickly running out of time, but in short, these models show great variation on how well they perform depending on what you measure. So we were looking at solution quality, efficiency, and reliability. And these were weighted differently. Solution quality was weighted the highest. This was basically were we able to find the shortest path, and if not, what the optimality gap was. Efficiency, how fast we were able to solve, and reliability, how many of the networks we fed to the solver that actually produced the shortest path. So what it came up with was a bidirectional A-star, and A-star is a version of Dijkstra's with some clever heuristics, making it able to handle graph with negative weights on the edges. The bidirectional part mean that it solved it from two different edges, and when they met, we say that the shortest path was found. It came up with some smart state pruning, saving a lot of information for every visited node, and this enabled the main A-star algorithm to prioritize search paths and prune away states that would never contribute to a better solution. We also had some heuristics. It ran one Dijkstra's at the very beginning. It was also used by the main A-star to prioritize search paths. And then also resource constraints checking. So if we were breaking a constraint very early on, it stops searching as it would never contribute to the best solution. So some very, very quick conclusions. Quite an interesting technology, merging fasting or faster moving areas such as AI with more traditional fields of mathematical modeling. Quite an exciting thing. However, unfortunately, not a success story like many other talks today. What we have today in our solvers are better, but as it continues to progress, we will keep an eye on this. There are several other experiments we would like to do. But yeah, in the interest of time, thank you all for listening.
Thank you.
Thank you so much for that super interesting presentation to both of you. Would you have some time for questions, if that's okay?
Of course.
So let's start off by, so you noted that this generative AI approach isn't quite yet better than what you have like currently. What specific breakthroughs in LLM capabilities would be required for this to outperform your current solvers, in your opinion?
I think like LLMs and having more targeted models would make a huge difference, and then also like the evolutionary framework could actually be the larger part. I don't think it's a secret that this tries to mimic Google's AlphaEvolve as closely as possible, and like some of the work they did, they improved matrix multiplication, which is quite impressive. It's like running it more structured way, making use of better suited frameworks, and I think primarily letting it run for a longer time, as this was time boxed to a couple of days, I think would make the largest improvement.
And next off is a question that follows. Have you explored, for example, gradient-based optimizations, including models for generating new columns, or maybe even reinforcement learning if the problem is non-differentiable?
The generation part of our solvers are mainly done by shortest path. We also have a few other generation like local search where we're doing minor changes. We have gradient solvers like gradient descent. It is more for finding the actual solution more than generating columns or rosters. But like one optimization or one optimizer, as we call it, contains several different methods that like work in combination.
Right. And with that, we want to thank you so much. And we also, of course, want to hand over these wonderful umbrellas as a thanks. And we also want to give you a warm applause. Thank you so much for being here. Thank you.
Thank you.